Hi, and welcome to Data Analysis on the MS 0754 plus 393. We used XRT data from the Swift Observing Telescope from September of 2014 for our particular object, which is an active galactic nucleus. As a group, we were tasked with looking at an active galactic nucleus, or AGN, with several tools to describe its composition and energy, and any other things we may come across that are novel. Uh, Data analytics can sometimes bring new things or insights to bear that you wouldn't necessarily expect. I personally was tasked in our group with the Swift XRT analysis using HEASOFT and its tools XSelect, XSpec, and of course DS9. Now, the Swift telescope uses a dozen or so nested mirrors feeding photons into a charged coupled device, uh, and it allows spectral emission monitoring of gamma burst events. So what we're looking for is the AGN to put off gamma burst, implying there is some sort of energy being emitted from these deep space objects. And we're looking specifically in the X-ray energy range. So we got our data from the archive, as of course the observation from 2014 is not exactly fresh in the minds and hearts of astronomers everywhere. Um, and this was accomplished at the website, shown on the next slide. And you see here the object coordinates are given by its name, and it has both the DSS optical image, which I thought was really interesting, and a non-Swift uh, processed X-ray image that shows the object itself. And we wanted all of these things, and most of what I did centered around uh, this secondary uh, telemetry point. This was the most intuitive part of the entire process. Once it was downloaded, we used, like I said, the XRT pipeline, which is another HEASOFT tool, to extract all of the data from the results of 0000805-95001. Really rolls off the tongue. And what we wanted to look at was the photon event file. And that gives you an image of the photons on the CCD as it is looking in its resolving space. And if you look at that in a linear, form, it's just specs. But if you look at it in a log form, you can see very clearly what is your observable object, what you want to study. So we download the event, then we process the event using DS9. Well, we create a background and a source region so that it can filter out what we don't want to see. And then we process the event into bin data. We analyze that data as a spectra. Then we graph that spectra with a fit that shows us how likely it is that what we're looking at is actually an observable object. And that gives us the flux of this particular event based on our statistics. Now, I used a chi-squared statistical fit with about approximately 1,000 iterations, as though I did not use a computer which used exactly 1,000 iterations. To maximize the likelihood, if you give it too much iteration, you can get declining results in confidence. So I did that, and our line of fit ratioed the data to see if there were emission lines at certain energy peaks that could give us an interpretation. Seen here is DS9 which is probably my favorite part of this entire data process, because as a visual learner, when I actually look at something and I can see, oh, that is obviously what I'm trying to look for, I find it very fulfilling. But we used this in getting the source counts, which would be that nice bright spot, and the background counts, which we would take from various areas of less dense photon counts, and then saving these regions into specific files are what we actually used in XSpec to do the math, which gave us our confidence. What we based all of our analysis on is the region files we generate from the event file seen here. And it looked like this, and that was just amazing to me because it was very hard to get here. And so there's strong lines at approximately 3.3 and 5.3 kiloelectron volts, and the flux or energy, the spectral energy density that I got was 1.0 times 10 to the negative 14, I believe, watts per meter, or for some reason it's given to me in the 10 to the negative 11 ergs per centimeter squared per second range. So we have a strong flux to analyze to understand exactly how much energy is coming off of our AGN. And we got an error range within 68% confidence, which, I mean, that's just great. I mean, it's not ideal. Ideal would be somewhere in the 90% confidence range. But, I mean, I'm an amateur. I'm the epitome of an amateur astronomer. What I thought, I was like really interested in looking through the 3.3 and 5.3 or 5.5 kiloelectron volt emission lines that I was seeing based off of the ratio to data down here. And what I found was something rather interesting based off of recent news. So in 2014, they took this data, and it wasn't analyzed according to the Swift archive until 2018. But in 2015, there was a paper published about observations of the new emission lines at about 3.5 in the X-ray spectra, which is exactly what I saw. Now, it doesn't discuss the 5.3, but it does say that the X-ray spectra in approximately 3.5 kiloelectron volts reported in several nearby galaxies and clusters are a possible interpretation would be a connection between this and the disruption of the standard model of physics. And I'm, of course, wearing my Fermilab shirt, where they just recently did the muon G2 experiment, which showed that the muon that we're seeing and observing with a high-powered magnet does not behave according to the classical interpretation of physics, and thus the standard model is the muon wobble helps show that perhaps the standard model is not what we're looking for. And I just thought that was amazing. Like, what a confluence of events. But thank you for your time, and any further questions can be emailed to me at csmith18@moorheadstate.edu.